Thank you. Welcome all to this webinar. So the first part deals with debugging modeling errors using model stability analysis in GSA. And I'm Ramaseshan Kannan. So you might have come across this warning when you run analysis in GSA, particularly elastic analysis. It warns you that the condition number of the stiffness matrix is 10 power 13, tells you it's high. Or worse, it might warn you, it might give you an error saying it's terminated due to matrix singularities, and you can no longer run the analysis, so can't get your results out. So we're going to be looking at why these warnings and errors arise. We call them ill conditioning warnings. And how can model stability analysis help us debug errors that lead to these errors, to lead to the ill conditioning? Okay. So the context to all of this, the reason why this becomes relevant is because all finite element computation that we do on modern desktop processors is done in so-called finite precision arithmetic. What that means is we've got real numbers that get approximated into a number which is of this form. So significant times base power exponent. So the form on the right is called a floating point number, and it's normally represented in a certain amount of precision. So your real number is going to be approximated to a certain degree of precision, and hence the name finite precision arithmetic. This cartoon gives a pictorial representation of what happens. So you got real numbers which are continuous, and they get approximated to floating point numbers which are discrete. And that leads to, gives rise to what we call round-off errors. To see how this manifests in a simple structural analysis problem, we've got a two-spring setup. The springs are in serial, and we've got a force acting on them, and we wish to find the displacements of the spring. So the stiffness matrix can be assembled quite easily, and it's of that form that you see on the screen. And then the forces become stiffness times the displacement. And therefore, the displacement is the inverse of the stiffness times the force. So far, so good. If we have values for the stiffness, say they're both 10 in some units, so the stiffness matrix looks like that, and the inverse would look like that. And so it would then be possible to solve for the displacement given that we know the force. But if we had a slight variation in the stiffnesses, so K1 is 0.001 and K2 is 10, so the second spring is 10,000 times stiffer than the first one. And if we were doing this on a hypothetical computer which supported just 4 digits of precision, your stiffness matrix in real numbers would look like that, but it would get approximated to that because we are working with just 4 digits of precision. So the first matrix, it's possible to solve for the displacements using it. The second one is numerically singular, because we have truncated the last digit. And so we won't be able to solve for the displacements, and this matrix is singular. So the accuracy of the solution that we're trying to obtain depends on the so-called conditioning of the stiffness matrix. And the conditioning is measured using the condition number cup K of the matrix. And it's given by this relationship here. I won't go into how we arrive at lambda n and lambda 1, but they are the eigenvalues, the extremal eigenvalues of the stiffness matrix. I won't say any more right now. But kappa k itself is bounded between 1 and infinity, mathematically speaking. So 1 is the best condition number you can have, and infinity is the worst, and that represents a singular matrix. However, because we are doing everything in finite precision arithmetic, we only have, we can only go up till 10 power 16 in condition number. And beyond that, or any condition number larger than that, is a numerically singular matrix. So the condition number gives us a rule of thumb for the number of digits of accuracy in our solution, and that's given by this relationship here. So the number of digits that are the maximum number of digits that could be accurate in a solution is given by 16 minus log of kappa. So the 16 comes from the fact that we have 16 digits of precision on the machine that we run GSA on, and in the way that software is written. So as you can see, anything that's greater than 10 power 16 would give you 0 digits of accuracy in your solution. And if you have something close to 10 power 16, say 10 power 15 or 14, then you have just 1 or 2 digits of accuracy in your answers. So a large condition number could be indicative of the presence of errors in your model. And these errors could be from a variety of sources. So you could have errors that result from idealizations. In your physical structure, you might have a simply supported beam, which doesn't have moment connections, and you might idealize it to a beam in this fashion, the model on the right, with the secondaries framing in and moments released. Now, in the physical structure, this might be stable, but in your finite element model, this wouldn't be stable because the primary beam is free to rotate about its axis because it doesn't have any rotational restraints coming from the secondaries, and also because it's pinned with supports. You could have errors from discretization. So if you have a mesh that looks like that, and you want to refine that corner where I've selected those elements, you might choose to refine it by splitting the mesh into smaller quad elements into smaller elements, but that might increase the condition number of the stiffness matrix. Easier to see in this example. So we've got cores modeled as sticks, the shear walls modeled as sticks, which are beam elements. And if, for example, this model had been imported from BIM or CAD, and the lines were faceted in such a way that you end up with really short beams, then because they're modeling cores, the beams also tend to be quite deep. So you essentially end up with disproportionate amount of stiffnesses in your stiffness matrix. And that's clearer to see when we look at the beam stiffness matrix. So you've got the EI over L cube terms over here. So when you have beams that are a few millimeters in length and a few meters in depth, you end up with really large terms in the stiffness matrix that can make it ill-conditioned. And you can also have errors from erroneous modeling itself. So in this instance, you have a flow slab supported by a column modeled using beam, and the flow slab model using quad-8 elements. Now, quad-8 elements in GSA don't have drilling degree of, stiffness in the drilling direction. And so if the bottom of your column is pinned, then effectively the column has no restraint against rotating about its own axis, and that can also lead to a singular model. So it's just down to incorrect data entry in this case. So in all of these cases, we could run model stability analysis to take a look at where these errors arise. So we go to GSA now. Okay, so I've got this model open here. Nice simple structure. I'm going to run static analysis, and it's thrown up an ill-conditioning warning. In fact, in this case, as you can see, it is singular because the condition number is larger than 10 power 16. So I would then run model stability analysis from the analysis wizard. Now, the choice of number of modes, it really depends on the nature of ill conditioning and the model you have in hand. So 10 is as good a default as any. So we start with 10 modes, and then as we'll see in a few moments, it tends to be an iterative process where you solve for a few modes, and then see if you can fix the conditioning and come back and solve again and see if the condition number has come down. I would normally leave the matrix shift unchecked, but it's something to use if model stability analysis has problems converging, because what we're essentially doing here is solving an eigenvalue problem in the background with an ill-conditioned matrix. So it is possible that on occasions it doesn't converge very quickly, and the matrix shift would be something to use at that point. High stiffness modes and low stiffness modes. So high stiffness modes are modes that arise, that could show you the error when your error is a result of disproportionate stiffnesses in your model. So for example, short stubby beams that we saw earlier, those would show up in high stiffness modes. Low stiffness modes are the modes that arise due to errors that are to do with certain parts of the model not being properly restrained or not having sufficient stiffnesses. And the vast majority of cases that we've seen where real conditioning arises are to do with low stiffness modes. So what I normally tend to do is run the model stability analysis with low stiffness modes and 0 high stiffness modes, and see if we can spot errors. If we cannot, then come back to this wizard and run it again, and then request for high stiffness modes as well. So on this occasion, I'm going to leave the high stiffness modes set to 0, and I'm going to hit finish. And while it's running, I thought I'd mention that model stability analysis, in contrast with the other sort of analysis options that GSA offers, is not really, it's only interrogating the numerical properties of the model. It's not looking at loads, and it's not a structural analysis as such. And even though it has a numerical basis, the way we use the results from model stability analysis is to look at them qualitatively rather than quantitatively. And then the two sets of results that it comes up with, we contour them, and then it's a question of poking around the model close to the elements that the analysis has highlighted. Right, so it's finished running. I'm now going to put this out of the way. Right. Oops. Okay. And I'm going to ask GS to contour under general element results. I've gone to the contour settings, and under general element results, I'm going to ask GSA to contour virtual energies. And immediately we can see that it's highlighted just one column, and it says it has a large virtual energy. So these energies that you see are relative in the sense that you don't see any other element being contoured in this on this plot. So all of them have very small virtual energies compared to the one that we see on the screen. The other set of results that model stability analysis returns are the eigenvalues under global results, under model stability summary. And I'll come back to these in a moment. So what the contour is telling us is that that element has a high virtual energy, and therefore the model definition in the vicinity of that element might have a low stiffness problem. Now, if I zoom in on this, I can quickly see that my toolbars are still hidden. Okay. So I can see that it's a quadrate element. And as I was saying earlier, they don't have drilling stiffness in the drilling direction. And then the column has a pinned support at the bottom, and so clearly this column is not restrained from rotating about its axis. If I then cycle through the other modes that I requested, we can see that it's highlighting each of the columns that have similar boundary conditions. So supported by coordinate elements at the top and pinned and the pin support at the bottom. Now, the table of eigenvalues. If you look at the table in fact, what I'm going to do is erase the results and run the analysis again for 15 modes so I can illustrate the point. But the table of eigenvalues, it tells us how many modes to examine, and the way we do that is by looking for a jump in the eigenvalues. So it's finished analyzing. So we can see that between the 11th and 12th eigenvalue, there's a jump in the magnitudes of the eigenvalues. So on this column, we have the eigenvalues of the stiffness matrix. And if we then contour modes 1 to 11, so we've been looking at the contours from mode 1 to 10. We're going to look at mode 11. So that's also a column that needs fixing. At mode 12, which has an eigenvalue which is not close to 0, so it's not as small as the 11th and the previous ones, indicates that the virtual energies are more evenly distributed in the model, and that suggests that the ill conditioning is to do with the first 12 modes, well, elements in the first 11 modes, and the ones beyond that are probably okay. So in this case, as I was saying, it's a matter of trial and error as to what we do to fix these errors. So I'm going to erase results and going to select nodes, all of these guys, and I'm going to modify them, and I'm going to restrain the rotation about the global ZZ axis. Then I'm going to try running modal stability analysis again. I think I left one out. So the column on the far corner is still pinned, but the condition number has already come down. So I'm going to go again and delete results and restrain that node as well, and run the analysis. So it's already reported an estimate of the condition number, and as you can see, it's come down drastically from 10 power 16 to 10 power 7, and that's made it a much better condition model than the one we started off with. And if you go back to the rule of thumb that we're looking at, initially we had 0 digits of accuracy in our solution, whereas with this, we might have up to 9 digits of accuracy in the displacements. And the eigenvalues are no longer close to 0. So eigenvalues close to 0 indicate a near singular or a very ill-conditioned matrix. So that was a quick demo of the feature. So because the errors can be quite arbitrary, it's not possible to compile an exhaustive list of all possible scenarios that could lead to these errors, which is why model stability analysis and debugging a model is an iterative process. There is no sort of step-by-step approach to, or a definitive step-by-step approach to fixing these errors, because it depends on what errors we're dealing with. But in our experience, we've seen models that are imported from BIM and CAD where lines are faceted they're faceted according to the requirements of the software that they were created in. And these can sometimes result in ill conditioning when imported into GSA. Releases on beams are another thing to watch out for. Sometimes we can have a string of beams that are all released, and it's not immediately apparent what's causing the ill conditioning. Mixing quadrates and beam elements, again, that's something we looked at, for example. Nodal connectivity errors. So you might have coincident nodes or nodes that are near coincident, and we could have adjacent elements connected to these coincident nodes, and one of them could be badly supported. It may not be apparent if coincident nodes are not turned on, and there could be a lack of stiffness in that part. And of course, constraints. So we need to be careful about how constraints are defined, especially joints and rigid constraints. You could have, you could connect two nodes or two parts of the model where the master doesn't have sufficient stiffness, and then that becomes insufficient stiffness of the slave as well. And because the size of the model, well, debugging a large model is more complicated than debugging a small one. So it's probably best to keep the condition number in check as we are building the model. So that way we won't have to, we wouldn't suddenly be faced with an ill conditioning problem in a large complicated model if you know, if you're aware of it right from the start. So in summary, it's necessary to ensure that stiffness matrix is well conditioned, and model stability analysis can be used to detect errors with causal conditioning.